Hello, my name is Andrew Wall. I'm an undergraduate student at Marshall University. The paper that I'm presenting today is titled Mutual Authentication Protocol for Internet of Drones. This is the outline for the presentation. I will start with the introduction and discuss the motivations for this research, and then I'll move on to the preliminary background. Basically, I'll discuss the two main features of the protocol, which are the physical unclonable function and the chaotic system. Then I'll discuss the proposed lightweight authentication protocol. After that, I'll explain the performance evaluation and finish up with the acknowledgement. Unmanned aerial vehicles, shortened to UAVs, and also known as drones, have emerged as a key part of the Fourth Industrial Revolution and provide an opportunity to revolutionize mobility networks. Drones are a popular choice for both military and civilian application, including disaster relief, filmmaking, photography, delivery, agriculture, and more. Now I'm going to share some data about drones. The sales of drones will surpass $12 billion in 2021, and the potential economic benefit of integrated unmanned airborne systems will generate an estimated $82 billion and create up to 100,000 jobs by 2025. So drones are becoming an important part in everyday life, and the industry is continuing to grow. Also, drone delivery services show enough potential that Amazon, Alphabet, Walmart, and other giants are hailing it as the future of e-commerce fulfillment. And the FAA approves UPS Flight Forward to be the first ever drone service operating as a commercial airline delivering medical supplies to local hospitals in the United States. UAVs are flying robots equipped with various equipment. They collect and analyze the physical phenomena and real-time information, and they can transmit data back to the ground station via wireless communication. Due to both financial and strategic information and value involved in aerial applications, the UAV system is vulnerable to attacks that target the cyber and/or physical elements, or the interface between them, or the wireless link, or even a combination of the multiple components. Here's an example of the vulnerability found in UAV systems. Since 2006, U.S. Customs and Border Protection has operated UAVs to patrol the United States borders with Mexico and Canada, watching for drug smugglers and unauthorized border crossers. In 2016, in January, the U.S. government confirmed that drug traffickers has hacked their UAVs to cross the U.S.-Mexican border illegally. An adversary can send unauthorized commands to the drone to take its control from ground station, and then catch and withhold the drone. This is exactly how the anti-drone gun operates, by hijacking the drone to have it go to an arbitrary waypoint. The two images show the Drone Buster, a gun that is designed to shoot signal interference to stop drones from operating. Investigating potential cyber threats against UAVs and designing security mechanisms are the top priority to ensure the cybersecurity of UAV applications, but there are a few challenges involved. The first being the existing standard primitives and cryptographic protocols are inefficient for small aerial drones. It has been proven that the drone's microprocessor and limited battery power struggle to handle these protocols. Thus, the lightweight protocols are the only suitable solutions to provide security services. Also, an adversary may attempt to probe or alter the circuit of the captured drone. Thus, UAVs should have tamper-resistant capabilities that enforce authenticated policies and cannot be overridden. To combat these challenges, we propose a lightweight mutual authentication protocol and its corresponding techniques to protect the communications between UAVs and ground station in an energy-efficient way. The basic idea of the protocol is that there is a UAV and ground station that use challenge response pair, or CRP, of a physical unclonable function, or PUF, as the initial condition of chaotic system to randomly shuffle the message, which piggybacks a seed to generate a secret session key. Here is some background information on physical unclonable function. A PUF can be regarded as a unique physical identity of a device, which is similar as biometric features to human beings. Integrated circuits have very slight physical differences due to variations in the manufacturing process. Alternatively, a PUF is defined as a circuit with an input-to-output mapping that depends on the unique characteristics of the physical hardware on which it is executed. For each PUF, an input query or challenge receives an instance-specific output or response, a process known as a challenge-response pair, or CRP. In general, a PUF can be represented as a function P in the following. CNR is the input challenge and output response of the PUF respectively. PUF can provide two valuable features for securing devices. One, the ability to dynamically regenerate a sensitive value using only public information. The challenge in this case is the public information, but without the correct PUF, it cannot be used to create the correct response, which is the sensitive information. The second feature is the ability to provide tamper resistance against various physical attacks. Using PUF, any attempted probing or altering of the PUF circuit would result in changing the intended output or could completely destroy the circuit. Now here's some background information on chaotic systems. A chaotic system is a dynamical and determined system with the intrinsic nature of nonlinear behavior, pseudo-randomness, broad spectrum, and sensitivity to initial conditions. Duffing map is a two-dimensional discrete time and dynamic system that exhibits chaotic behavior, and it's the system we'll be using for this protocol. It is widely known to display chaos for certain parameter values and initial conditions. Duffing map contains a single cubic term and is expressed below. A and B are constant parameters, usually set to A equals 2.75 and B equals 0.2 to create chaotic behavior. The output of the Duffing map highly depends on the initial condition represented by x0 and y0. The Duffing map shows chaotic behavior after 10,000 iterations, where x0 equals 0.5 and y0 equals 0.5. Any change in the initial condition will affect the plot of these points. The figure on the top right shows the Duffing map after 100 iterations with x0 and y0 both equal to 0.5. The figure on the bottom right shows Duffing map after 100 iterations with x0 equaling 0.6 and y0 equaling 0.4. If you look at the areas highlighted with the red boxes, the specific points are completely different after just slight variation in the starting values. And now I would like to explain our proposed lightweight authentication protocol, starting with the network model. In our model, there are two participants, the UAVs and the ground station. Each UAV is equipped with one PUF. During the system deployment phase, the ground station obtains an initial challenge response pair from each UAV securely. So, the ground station stores the ID and the initial challenge response pair for each UAV, while the UAV does not store any secret information. That way, if an attacker is able to capture a UAV, the attacker will get no valuable information from the UAV since it does not store any important information. I will explain the lightweight authentication protocol using this figure. In this figure, there are vertical lines and horizontal lines. The vertical lines represent time, while the horizontal lines represents communication between the UAV and the ground station. There are also these boxes filled with text. These boxes filled with text represents the operations that the UAV or the ground station are performing. To begin communication, the UAV will send its ID and a randomly generated number to the ground station. The ground station will then attempt to locate the UAV ID in memory and then retrieve the corresponding challenge response pair and then generate a random number called PRFGS. It will then create a plain text message using the UAV ID, the randomly generated number from the UAV, and then its randomly generated number. It will then encrypt that plain text into ciphertext using Duffing map to shuffle its bytes and uses the challenge response pair as the initial conditions. After creating the ciphertext, it generates a MAC verification code. And then it will send the challenge, the ciphertext, and the MAC verification code over to the UAV. The UAV will use the challenge and its PUF to generate the response, and then restore the plain text message using the challenge response pair on the ciphertext. From the plain text message, it will obtain the randomly generated number from the ground station and then verify the MAC that the ground station sent it with a MAC that it generates using the ciphertext, the challenge response pair, and the randomly generated number from the ground station. It will then generate its own randomly generated number referred to as PRFX. Using PRFX and PRFGS, it will create a new challenge and a new response. It will then create another plain text message using its ID, the randomly generated number it just generated, the randomly generated number from ground station, and the new response. It will then encrypt that plain text message into ciphertext using duffing map to shuffle the bytes and using the original challenge response pair as the initial condition. It then creates a MAC verification code. It sends the ciphertext message and the MAC verification code over to the ground station. The ground station then uses the challenge response pair to restore the plain text message. It obtains the randomly generated number from the UAV from that message, verifies the MAC with its own that it creates using the ciphertext message, the challenge response pair, and the UAV's randomly generated number. It then creates the new challenge using the UAV's randomly generated number and the ground station's randomly generated number, and informs the new challenge response pair and saves it to memory. At this point, both the UAV and the ground station has the necessary randomly generated numbers to create the session keys and establish a secure connection. Now for the security analyst. The protocol is designed to defend against different security attacks, including cloning attacks, tampering attacks, man-in-the-middle attacks, and replay attacks. The UAV and the ground station don't use any computationally intensive cryptographic algorithms, which significantly reduces the computational cost of the authentication protocol. Each communication session will have a different challenge response pair. The exchange messages will expire when the communication session ends. And now for the experimental evaluation. We plan to conduct simulation experiments using Network Simulator OMNet++ to evaluate the performance of the proposed approach. The metrics that we're using for the performance test are the computational cost, the memory usage, the energy consumption, and the communication overhead. Now for the acknowledgement. This research was supported in part by West Virginia Higher Education Policy Commission Division of Science and Research Grant and NASA West Virginia EBSCOR grant. If you have any questions, please feel free to contact me via email. Thank you.